Welcome to The Explainer. Today, we're taking the wild, dangerous highway of the open internet and turning it into a highly secure, armored tunnel using the fundamental building blocks of IPsec VPNs. If you've ever wondered exactly how your most sensitive data manages to travel safely across public networks without being intercepted, tampered with, or completely exposed, well, you're in the right place. Let's get right into it. Let's just quickly run through our roadmap for this explainer. We'll be hitting 1. Defining secure VPNs. 2. Ensuring data integrity. 3. Verifying source authentication. 4. Maintaining confidentiality. 5. Advanced cryptography, specifically Suite B. And finally, number 6. Juno's configuration components.
All right, Section 1, Defining Secure VPNs, the problem and the solution. So a secure VPN essentially builds a tunnel right across the public internet. It does this by encapsulating and encrypting an IP packet so it can safely travel from one private network over to another. Think of encapsulation kind of like putting your original IP packet inside a secondary, heavy-duty secure envelope before it ever even touches the public network. This is exactly what allows a device sitting at, say, IP 10.0.0.0.5 to talk securely to a server over at 10.1.20.3, even though it's traversing completely public IP space to get there.
But listen, just slapping an extra envelope on your data? Yeah, that's not going to cut it. To actually build an impenetrable tunnel, we have to rely on a triad of core security concerns: integrity, confidentiality, and source authentication. Basically, everything we do when building IPsec VPNs comes right back to defending these three pillars. Which brings us to Section 2, ensuring data integrity, protecting the actual payload.
We lock down this integrity using strong hash functions. Now, a solid hash function has to follow a couple of non-negotiable rules to actually be useful for us. First off, it absolutely must be strictly one-way, meaning a bad actor cannot reverse engineer the original data just by looking at the hash value. Second, it has to be highly collision resistant. A collision is what happens when two totally different input values somehow spit out the exact same fixed length output. We want to avoid that completely, because if a hacker modifies even a single bit of your payload, we need that resulting hash to change drastically, immediately sounding the alarm that something's wrong.
So how does this actually look in practice? Well, it's basically a 5-step dance between the sender and the receiver. First, the sender runs the data through the hash algorithm, creating a hash value. They append that hash to the data and send the whole package across the network. Now, when the receiver gets it, they separate the original data from the sender's hash. The receiver then takes that original data and runs it through the exact same hash algorithm, entirely independently. Finally, they compare their brand new calculated hash against the one the sender provided. If those two match up perfectly, boom, we know for sure the data has not been messed with.
Okay, so we know that data hasn't been tampered with, but how do we definitively prove who actually sent it? That brings us to Section 3, Verifying Source Authentication.
Enter HMAC, or Hash-Based Message Authentication Code. This brilliantly introduces a pre-shared key, a secret known exclusively to the sender and the receiver, directly into that hashing process we just talked about. Before running the hash function, the sender appends this secret pre-shared key right to the data. Then it travels across the network. The receiver takes the data, grabs their identical copy of that secret key, appends it, and hashes the whole thing. If the final hashes match, it proves two things at once. The data is completely unaltered, and it absolutely, without a doubt, came from a valid source who holds that secret key. When you're actually setting this up in Junos, you've got a really wide array of hashing algorithms at your disposal. During the initial tunnel setup, what we call Internet Key Exchange, or IK, phases 1 and 2, you have a whole spectrum of choices. You can go with older standards like the 128-bit MD5 or 160-bit SHA-1, or you can step it up to highly robust algorithms like SHA-256 and SHA-384. Generally speaking, a larger bit length means a larger output, and a larger output drastically reduces the probability of a hash collision, which makes your integrity check that much stronger. All right, so we've locked down the integrity, we've verified the origin, but what about keeping the actual contents hidden from prying eyes? Section 4, Maintaining Confidentiality. Confidentiality is all about encryption. And a super efficient way to handle large amounts of bulk data is symmetric key encryption. In this model, you use a single secret shared key. The sender uses it to lock or encrypt the original data into ciphertext. Then, that exact same key is used by the receiver to unlock or decrypt it back into readable plaintext. Because you're just using one key for both actions, it's computationally really fast, perfect for heavy network traffic.
On the flip side, we have asymmetric or public key encryption. This operates a bit differently. It relies on a mathematically linked key pair. You have a public key that you can freely share with anyone, and a highly guarded private key that you literally never share. If a sender encrypts data using your widely available public key, only your secret private key has the math required to decrypt it. This creates a vastly stronger form of secure exchange because that private key never ever travels across the network. But keep in mind, it does come with a higher computational overhead that scales with the size of the keys. Looking specifically at Juno's support for symmetric encryption, you've got a pretty vast spectrum to choose from. It scales all the way from legacy algorithms like 56-bit DES up to massive 256-bit AES algorithms. You'll also notice Juno supports different operating modes, things like CBC, which is cipher block chaining, and GCM, or Galois/counter mode. This flexibility is great because it lets network admins perfectly balance their security needs with their processing speed. Of course, as threats on the open internet evolve, our armor has to evolve right alongside them. Section 5, Advanced Cryptography, Suite B. So what exactly makes Suite B so special? Well, it's a really rigorous set of unclassified algorithms developed by the NSA. It's specifically designed to protect the absolute most sensitive data out there. We're talking national security, healthcare records, financial data, and top-tier intellectual property. And beyond just having incredibly strong math, it uses a layered encryption approach that enables vendor-neutral integration, meaning highly secure, totally diverse devices from different manufacturers can all talk to each other seamlessly, and most importantly, safely. One of the coolest things about Suite B is how it uniquely leverages elliptic curve cryptography, or ECC, which is just vastly more efficient than older standards. Let me put this into perspective. To achieve a security strength of 112 bits, you only need a 224-bit ECC key. Now compare that to a massive 2048-bit key required to get that exact same security strength if you're using RSA. It's a huge difference. ECC makes our encryption significantly harder to crack while keeping the computational load remarkably light and fast. Okay, let's take all of these theoretical pillars we've been talking about and see how they actually look in a practical environment. Section 6, Juno's configuration components. When a device supports Suite B, the algorithms are configured in a really strict, logical four-step progression. We start at the top by defining the IKey proposal, and then we tie that directly to an IKey policy. From there, we move down and configure the IPsec proposal, and finally, define the overall IPsec policy. This structured, step-by-step approach builds the secure tunnel from the very first key exchange all the way down to how the bulk data itself gets locked up. During that initial IK phase, you as the administrator have incredibly granular control. You can manually configure advanced authentication methods, like ECDSA signatures and strong SHA-256 hashing, alongside modern Diffie-Hellman groups, like 19 and 20. Or, if you need a faster deployment, you can just lean on Juno's predefined policies. Actually, just applying the predefined Suite B GCM 128 policy handles a massive chunk of the complex configuration for you, right out of the box. Then moving into the IPsec phase, the configurations lock down the actual bulk payload data using heavy-duty AES GCM encryption algorithms, scaling all the way up to AES 256. What's absolutely crucial here is pairing this with perfect forward secrecy keys, utilizing groups 19 and 20. Perfect forward secrecy, or PFS, is an incredible feature. It guarantees that even if a key is somehow compromised way down the line in the distant future, past recorded network sessions can never be decrypted. It is the ultimate guarantee for maximum long-term confidentiality. We've seen how hashing, HMAC, and complex asymmetric encryption all weave together to create this incredible digital armor, protecting our data from the wild west of the open web. But going through all of this leaves us with one pretty provocative thought. As computing power continues to grow exponentially, especially with the dawn of quantum computing right there on the horizon, what is the next evolution of this tunnel going to look like? How long will our current cryptographic Suite B actually remain impenetrable? It's a question every network architect needs to be asking themselves today. Thanks so much for learning with me, and keep exploring.